Hello my dear students. So before we start with today's class, let us have a look at a special kind of number. So the number is like this: 3 to the power of 3 plus 4 to the power of 4 plus 3 to the power of 3 plus 5 to the power of 5. This is equal to 3, 4, 3, 5. Got it? Very interesting, right? 3 to the power of 3, 4 to the power of 4, 3 to the power of 3, 5 to the power of 5 is equal to how much? 3, 4, 3, 5. Such type of number is called as Munchausen number. So what is a Munchausen number here? Munchausen number is nothing but a natural number where on the left hand side the natural numbers are raised to its own power and there is a sum between two numbers. So that is equal to 3. You all to Vista's learning. In today's session we'll be starting with the next topic of class 11th, which is called as complex numbers and quadratic equations. So here which number have we seen? We have seen a Munchausen number, correct? Now what we are going to see, students, is the complex numbers and quadratic equations. So first we'll be having a look at complex numbers. Once we finish this entire synopsis, then we'll be moving on to next one, that is quadratic equations. Alright, so let us start with complex numbers. Here we have introduction first. Now students, in introduction, in your class 10th, while we were solving quadratic equations, we had a term called as discriminant, correct, which is denoted by capital D, correct? And what is this capital D? B square minus 4AC, right? If D is equal to 0, how are the roots? The roots are real and equal, correct? And if the discriminant is greater than 0, then how are the roots? The roots are distinct, which means different, and real. Equal means the roots are equal. Now, but when we had D lesser than 0, what we had written here? No real roots. Understanding? Equal to 0, real and equal. Greater than 0, distinct and real. Now when it is lesser than 0, what is D? Discriminant. When the discriminant is lesser than 0, what is happening? We are writing there are no real roots, which also means there are imaginary roots. Understanding? So imaginary roots. So this type of quadratic equation which is having discriminant lesser than 0, which type of roots will they have? They will be having an imaginary roots. So can you tell a number, students, which is, okay, so complex number, this is denoted by Z. Okay, this is also denoted by Z, X plus IY. Okay, so this is how, what is this? This is the standard way, okay, standard form of complex numbers. Standard form of complex numbers where X is the real part and Y and I and Y, this is what? This is the imaginary part. Okay, so if example Z is equal to X plus IY, if we write it like this, RE of Z is equal to X, IM of Z is equal to Y. Imaginary part IM, real part RE of Z. Z is nothing but what? Complex numbers. So this is just the introduction. So why are we using complex numbers? So whenever we get determinant lesser than 0, we have to find the solution, but there are no real roots. Then which type of roots are existing there? Imaginary roots are existing. Understood? Moving on to the next one. So students, see this. This is the representation of numbers. Okay. So initially, which number do we have here? Natural number n, correct? So here we have natural number n. What are the natural numbers? 1, 2, 3, and it goes on like that. Correct. Next we have, after n, we have natural, so this is natural number starting from 1. Whole numbers, they are starting from where? They are starting from 0. So under whole numbers only we are getting what? Means natural number is a subset of whole numbers. Correct. So after that, so in to the inner side or to the core we have natural numbers. Outside that we have whole numbers. What is extra here? 0 is extra. Okay, moving on to the next one. Z. So what is this Z? Whole numbers are starting from 0, right? Whole numbers are starting from 0. What is to the left side of 0 then? To the left side of the 0, we have the negative numbers, correct? Minus 3, minus 2, minus 1, 0, then 1, 2, 3 and so on, correct? So what are Z here? Z are nothing but integers which is consisting of both negative as well as positive values. Okay, moving on to the next one. Rational numbers Q. So what is rational number? Any number which can be expressed in the form of P by Q, where Q is not equal to 0, that type of number is called as what? A rational number, correct? Moving on to the next one. Real numbers. So there are few irrational numbers also, right? Like root 2. You cannot express this in the form of P by Q, where Q is not equal to 0. Okay. So in order to express these numbers, which are we taking? We are taking real numbers. And outside this, what do we have, students? See, which color can you see outside this? Outside this, we can see the black color, right? That black color is nothing but called as complex numbers. Complex numbers is consisting of all these sets. Real number is consisting of only these sets. Rational numbers, these sets. Whole numbers, only n. And n itself is consisting n only. So these are the representation of numbers. Natural numbers, whole numbers, integers, rational numbers, real numbers, and finally we have what? Complex numbers. So this is the classification of numbers. One more number we saw in the very beginning, right? That is Munchausen number. Hope you remember that. Okay, moving on to the next one. Algebra of complex numbers. So we came to know what is complex numbers, right? Complex numbers is the numbers which is consisting of all the numbers. And that complex number is denoted by the letter Z, which is equal to x plus iy, where x is the real part of a complex number and iy is the imaginary part. So that is complex number. Now we are going to see what? Algebra of complex numbers, which means the very first one, addition of two complex numbers, division of two, difference of two complex numbers, multiplication of two complex numbers, division of two complex numbers, and power of I. What is this I? We will discuss that. In today's session, we will be seeing addition, difference, and multiplication. Understood? So one more thing, that is division and power of I, we will be covering that in our next session. So in today's session, we will be doing only these three. So quickly jumping into the addition of complex numbers, students. So what is addition of complex numbers? So there are two complex numbers now. Z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. Now z1 plus z2 will be equal to what? Z1 plus z2 will be equal to x1 plus x2 plus I of y1 plus y2. Means what is happening here? The real part is getting added with the real part only. See this, x1 plus x2, and the imaginary part is getting added up with the imaginary part only. So that is I, you have taken out common, y1 plus y2 inside the brackets. So this is nothing but addition of complex numbers. Very simple. So this is a very small demonstration. So we'll see further. The addition of complex numbers satisfies the following properties. How do we add complex numbers? Okay, that has been shown here. So addition of complex numbers satisfies which all properties? That is what we are going to see next. The closure law. What is closure law, students? Which means if you add two complex numbers z1 and z2, this will be equal to what? Another complex number called as z3. So when you add two complex numbers, what are you getting the result as? The result also we are getting it as a complex number only. So this law is called as what? This law is called as closure law. This closure law is being satisfied by addition of complex numbers. Got it? Moving on to the next one. Commutative law. Commutative law is nothing but like this, students. If z1 plus z2 is equal to z3, then z3 is equal to z2 plus z1 as well. Correct? z1 plus z2 is equal to z3, then z3 is also equal to z2 plus z1. So this is nothing but called as what? A closure law. Sorry. Commutative law. Closure law is this. This is commutative law. Moving on to the next one. Associative law. So here we'll take three complex numbers. So students, here for associative law, z1 plus z2 plus z3 is equal to z1 plus z2 plus z3. These LHS will be equal to RHS. This law is called as what? This law is called as associative law. Okay, moving on to the next one. Existence of additive identity. Now students, what is additive identity? Additive identity is a number. If any number is added to that, you will be getting the same number. I'll just repeat that once again. Additive identity is a number to which any number you add, you will be getting the same number again. So what is additive identity? Additive identity is always 0. To 0 you add any number, add 999. So 999 plus 0 will be equal to 999. correct? So what is 0 called as? 0 is called as additive identity. Got it? Moving on to the next one, existence of additive identity. Next, existence of additive inverse means what? Inverse it. So if z is equal to x plus iy, what is the existence of additive inverse? Minus x minus iy. So what will happen if you add them both? So let us take it as z. This will take it as z1. So z plus z1, which is equal to 0. Additive inverse. Additive identity. Additive identity is 0. Very simple. Additive inverse is minus x minus iy. This is called as what? Additive inverse, which means if you add the complex number or any given number to its additive inverse, the answer must be equal to 0. So this is called as what? Existence of additive inverse. Understood? Moving on to the next one. So these are basics of complex numbers. Means what? We just now saw how to add complex numbers and what are the properties that is being satisfied by the addition of the complex numbers. Okay, moving on to the next one. The next heading is difference of complex numbers. Same thing, if z1 is equal to x plus iy, x1 plus iy1, and z2 is equal to x2 plus iy2, then z1 minus z2 will be equal to x1 minus x2 plus I of y1 minus y2. This is what, students? This is our difference. Means the real part is getting subtracted by the real part only, as you can see here. The same way, imaginary part is getting subtracted by imaginary part only. So this is nothing but called as what? Our difference of two complex numbers. Okay. So here we are seeing the operation by using some variables only, right? But when we start doing our problems or examples, we'll be taking some real numbers and we'll be solving this further. So what is this I? That is not yet explained yet. I'll be explaining this very soon. Okay, do not worry. Moving on to the next one. Multiplication of two complex numbers. Same thing, students. z1 is equal to x1 plus iy1. z2 is equal to x2 plus iy2. Then z1 dot z2. So here what is happening? This x1 is getting multiplied with x2 as well as iy2. Okay, what happened previously, students, in addition and subtraction? In addition and subtraction, the real part was getting added up with the real part only and the imaginary part was getting added up with the imaginary part. But what is happening in multiplication now? This real part is being multiplied with the real part as well as the imaginary part. Did you understand the difference? So this is nothing but multiplication of complex numbers. So there are a few properties which are satisfied by multiplication of complex numbers as well. So following our first one, closure law. If z1 is a complex number, z2 is a complex number. If you multiply these both complex number, you will be getting a complex number again. This property is called as what? Closure law. Moving on to the next one. Commutative law. z1 dot z2 will be equal to z2 dot z1. Same thing. There we were using plus sign. Here we are using dot, which is nothing but what? Multiplication. Correct. Moving on to the next one. Associative law. So associative law, z1 z2 of z3 is equal to z1 z2 z3. Associative law. Moving on to the next one. Existence of multiplicative identity. Now students, what was additive identity? Any number you add to that number, you'll be getting the same number. Multiplicative identity is any number you multiply with that number, you should get the same number. So what is the multiplicative identity here? Multiplicative identity is 1. So any number you multiply with 1, 999 into 1 is equal to 999 only. Correct? 99 into 1 is equal to 99 only. So this is existence of multiplicative identity. So there is also called as existence of multiplicative inverse. And what is that multiplicative inverse? Z inverse, which is equal to 1 by Z. Now you take the students. You have Z here already. So what is Z? Z1 will take. What is the multiplicative inverse of Z1? 1 by Z1. So when you multiply both of them, you are getting how much? 1. Correct. In additive identity, in additive inverse, when you add two numbers, you are getting 0, right? In multiplicative inverse, when you multiply two complex numbers, you must be getting 1. So that is nothing but existence of multiplicative inverse. The very last property, distributive law. So here, Z1 of Z2, Z3, this is equal to Z1, Z2 dot Z1, Z3. Okay, so this is nothing but what, students? Z1 plus here. Okay, so there is a plus. Z1 into Z2 plus Z1 into Z3. So these both will be equal to each other. So this is nothing but what, students? Are distributive law. So these are whatever session we had until from the beginning until now. This is introduction to complex numbers and the algebra of complex numbers. Once again, very quick summary. What is complex numbers? There are few equations which we cannot solve. For example, x square plus 1 is equal to 0. This is a quadratic equation. If you find out the discriminant of this, the discriminant will be lesser than 0, which means there are no real solutions. That implies what? That implies there is some imaginary solution. So that imaginary number mixed up with the real number, that combination. So for example here, this is a real number, this is an imaginary number. The combination of these both is nothing but called as what? Complex numbers. We had seen some algebraic functions or operations on complex numbers, that is addition, subtraction and multiplication. So we'll be ending the session here, students. Stay tuned to Vista's learning. Thank you.